A 0.1 molar weak acid has a pH of 3. Find Ka. If we want to find Ka, we first need to know that a weak acid partially dissociates into H plus and A minus. And the Ka equation is going to be our H plus concentration multiplied by our A minus concentration divided by our initial complete acid concentration. So if we are given pH, the first variable that we can solve for is going to be our H plus concentration. We know that H plus is equal to 10 to the negative pH. So in this case, it'll be 10 to the negative third. That gives us an H plus concentration of 1 times 10 to the negative third molar. Next, we need to make an ice table. So if we set up our ice table, if we look at our initial concentrations, we know we have 0.1 molar of our HA, of our acid. And since our reaction didn't go through yet, we're going to have 0 H plus and A minus. Nothing dissociated yet. Our change, as we just determined, is going to be 1 times 10 to the negative third, or 0.001. So from our initial, we're going to take away 0.001. And in our products, we're going to gain 0.001 for each product. Our equilibrium now is going to be 0.099 of our HA, 0.001 of our H plus, and 0.001 of our A minus. Now we can plug these three values into our Ka equation. So we have our Ka is equal to our H plus concentration, which we know is 0.001, multiplied by our A minus concentration, which is also 0.001, and it's going to be divided by our initial acid concentration, which at equilibrium is 0.099. When we do this math, we get a Ka value of 1.01 times 10 to the negative fifth, and this is not going to get a unit. Let's look at another example. So here we have a 0.25 molar weak acid with a pH of 2.8, and again we need to find Ka. We can start this off just like we did before. Since we have the pH, we can automatically get the H plus concentration. So our H plus is going to be equal to 10 to the negative 2.8 power, which is just 1.58 times 10 to the negative third molar. Again, we have to set up our ice table. We're initially starting with 0.25 molar of our HA and 0 H plus and 0 A minus. Our change we just determined to be 1.58 times 10 to the negative third, so we're going to subtract that from our HA. And we're going to add it to our H plus and our A minus. So these two values are the same, and we can just drop them down. And the HA is going to be 0.25 minus that change, which is going to give us 0.2484. Now if we plug this into the Ka equation again, we'll get Ka is equal to 1.58 times 10 to the negative third. And since this is the same for both H plus and A minus, we can just simplify and square it. That's going to be divided by 0.2484, giving us our Ka value of 1.01 times 10 to the negative fifth. Let's look at one more example. So here we have a 0.05 molar weak acid with a pH of 4.2. We need to find Ka again. So we can get our hydrogen concentration, or H plus, by doing 10 to the negative 4.2 power, that's our pH. We get 6.31 times 10 to the negative fifth molar. You can do the ice table on your own and test out your answers to see if they compare, we should get the 6.31 times 10 to the negative fifth for the H plus and the A minus. So if we insert that into our Ka, we get our 6.31 times 10 to the negative fifth. We'll just square it, and that should be divided by 0.04994, giving us a final Ka value of 7.96 times 10 to the negative 8th power. But what if we went the other way? If we have a 0.1 molar weak acid with a Ka of 1.8 times 10 to the negative 5th, what is the pH? So we're going to have to set up our ice table again, and we'll put our initial concentration of our 0.1 molar, our 0 and 0, since our reaction hasn't started yet. And for change, now here is where we would have put our H plus concentration, which we could have gotten from the pH, but we don't have that. So we don't actually know what the change is. So we can just say that we're going to subtract X from HA. And if we're subtracting X from HA, that means H plus and A minus are both gaining that same amount. So our equilibrium for our HA is going to be 0.1 minus X, and then for H plus and A minus is just going to be X. So if we insert these values now into our Ka equation, we should get X squared divided by 0.1 minus X. Here, we can plug in Ka, since we know it's 1.8 times 10 to the negative 5th. Now instead of solving the full quadratic by doing this cross multiplication and then getting the trinomial, we can use the small x approximation. Since x, as you saw from the previous examples, is going to be so small, we can say it is essentially going to be the initial concentration. So we can just remove the minus x and assume that is going to be very close to the initial concentration of 0.1 molar. Now this makes our problem solving a lot easier. We can still cross multiply here, and we'll get x squared is equal to 1.8 times 10 to the negative 6th. When we square root both sides, we get x is equal to 1.34 times 10 to the negative 3rd. Now this is not going to be our pH. If we look at what x actually is, it's what our change was. And we know our pH and our proton concentration, which is just that plus x, are related to each other, and we can solve one if we have the other. So this x, this 1.34 times 10 to the negative 3rd, is that proton concentration. We know pH is equal to negative log of our H plus concentration, which we found to be 1.34 times 10 to the negative 3rd. And that gives us a pH of 2.87. Let's look at one more example. If we have a 0.2 molar weak acid with a Ka value of 4.5 times 10 to the negative 6th, what is the pH? So we're going to set up our ice table just like before. Our initial concentration is 0.2 for our HA, 0 for our products. We know we're going to be subtracting some amount that we don't know yet, and that same amount is going to be added to our H plus and A minus, giving us the same equilibrium, except this time it's 0.2 minus X, and H plus and A minus are still going to be X. So now if we look at our Ka equation, we can plug in 4.5 times 10 to the negative 6. That's our Ka value that was given. That's equal to X squared, and that's simply our H plus and A minus, since they're multiplied together and the same amount. We can just write X squared as a shortcut, divided by, now it should be this 0.2 minus X, but we can use that small x approximation again, and just assume our equilibrium is going to be 0.2, and we're just not going to subtract that x. So once we cross multiply once again, we'll do 4.5 times 10 to the negative 6 times 0.2. That gives us 9.0 times 10 to the negative 7th. That's equal to x squared. When we square root everything, we get x is equal to 9.49 times 10 to the negative fourth. Our pH then is negative log of this answer, because this is our H plus concentration. So negative log of 9.49 times 10 to the negative fourth. That should give us a pH value of 3.02. Thank you for watching.